Here in our project, there's a wave that travels through the slinky. The amplitude of the wave is what knocks over the blocks. Waves are ways that energy travels through medium. And in our project, the slinky here is what the medium is, and the energy is traveled through the wave, and the amplitude is where the energy is coming from. The wave traveling through the slinky is a transverse wave. This means that the amplitude is completely perpendicular to the direction that the actual wave is traveling in. The wave is traveling that way along the slinky, but the amplitude is actually going towards these blocks.
You can see in our project we have an inclined plane. There are 4 forces acting on the ball during this project. The impulse from the block begins the ball's motion down the slide, where it encounters static friction. The impulse from the block only acts on the ball initially and isn't constant throughout the journey. Static friction, on the other hand, is constantly acting on the ball, but the force of it is very small. The other forces involved are gravity and the normal force. The normal force is perpendicular to the surface of the slide, and the weight is pointing straight towards the ground. The normal force is from Newton's third law, which states that a force on an object must be equal in opposite. In this case, the force of the ball is counteracted by the normal force, which is pointing away from the plane. The normal force and the weight in the y direction can cancel each other out because there is no acceleration in the direction of the y-axis. The ball has a change of momentum going down the slide due to the acceleration of gravity. As you can see, we have a pendulum in the middle of our project. So when the ball attached to the pendulum is where it is right now, at the bottom of the ramp, it is all potential energy, which can be found by the equation mgh, the mass, the acceleration of gravity, and the height. Now when this ball comes down the ramp and hits this ball out of its position, as the pendulum is moving, since mechanical energy is conserved, the sum of the kinetic energy and potential energy at any given point should be the same throughout its swing. And when the ball is right down here in the middle, it is all kinetic energy, which can be found by the equation 1/2 mv squared with the mass and the velocity.
Here in our project, there is center of mass exhibited by this green block balancing on this red one. Its center of mass is directly in the middle because it is a uniform block, and so all of the mass is completely averaged out to be in the center. When this green block is hit by the pendulum swinging, some of the energy is transferred into the block, moving it forward, knocking it off of the center of mass. When it is knocked off the center of mass, it falls. In our project, there are lots of places where there are impulses and instances where momentum is playing a role. An impulse is a force felt over a certain period of time and is shown by the equation force times delta t, which is just the change in time. That gives you the magnitude of an impulse. An impulse can also be defined as the change in momentum, which is also mass times a change in velocity. And the first impulse we see is here with this block where it gets hit by the slinky. It experiences a pretty large impulse as the force is being distributed over a short period of time. It then comes here to this block and it keeps hitting to the ball. The ball takes the impulse and is converting it into kinetic energy where it has momentum going down this ramp. The momentum is then carried through the pendulum onto these blocks. Blocks here experiences an inelastic collision with the next one. They don't bounce away, they actually just continue to fall onto the next block. Even though they don't bounce away, the momentum is still conserved because of the law of conservation of momentum. The mass might be growing, but the velocity is changing to accommodate for the different mass.
Project, we use magnets. Magnets create magnetic fields in the space around that object, and in our case, we have them interact with each other, and we use 2 like charges and put them near each other so they would repel, sending the train down that ramp. A magnetic force is caused by its magnetic field and the direction it is pointing in. What dictates the direction of the magnetic field is the positive or negative charge. A positive charge is a lack of valence electrons, while a negative charge is an excess of them. If, for example, we had 2 positive magnets, this and this, the direction of the magnetic field would be pointing away from each other, and consequently the magnets would repel.